So we start with chapter 15 today, right?
Let me say, I don't remember the number of the chapter. 22.
22, okay.
Yes. So the chapters in between 15 and 22 is more like some of them are like heuristic algorithms, and also some of them are a little bit more advanced data structures like B tree. B tree, B plus tree, and so we don't spend much time on it. It's definitely that topic is definitely beyond the level, the undergraduate level. So yes, we just focus more on this part. So the plan is that so for the rest of the semester, including this one, we still have 6 weeks left. So we have 6 weeks remaining, and we're going to spend 4 weeks on lectures. And so 1 week on review to help you prepare the final exam. And 1 week is the last week we'll take the final. Okay, so this is our plan. So all the 4 weeks are going to be focusing on the graph bar. So the graph and the graph data structure and the underlying algorithms of that associated with the graph. So okay, and so that will be that's the plan for the remainder of the semester. Okay. So in the chat I see someone saying that I miss having class. I mean, wow, you are so motivated. Okay, yeah, that's great. When I was a student, it's like when I keep having classes, I want to have a break. But if I have the break for too long, maybe for 2 weeks, then I miss the class. Yes, so yeah. But it's I when I was a student, I remember that I really enjoyed the summer, because in the summer you don't have to take a lot of classes. Usually you only take 1 or 2 classes, or and the workload is much lighter than the spring and fall. So during that time, like I was studying, but I didn't overload myself. So yes, I got time to go to gym, to watch a couple of movies. So that's really enjoyable. Okay, I also see a chat saying that I've been lit coding all of last week. Easy questions are all right. Medium and hard are beyond my comprehension at the moment. Yes, if you're doing lit code to brush up your programming and prepare for the coding interviews. So my suggestion is that for any question, if you after spending two hours you don't have any clue, just go for the answers, and you learn from the answers. So that's how I did, and I do acknowledge that some of the questions are so hard. So even though you're giving the answer, it takes you like 4 or 5 hours to digest the answer. So yes, then that's good. So okay, and so today we will learn the last data structure named graph, and learn two algorithms associated with graph. So previously we said, if you remember, we said that data structures and algorithms are always they always come in combinations. So if this is the data structures, then this is the algorithms. So for example, the first data structure that we learned is like stack and queue. So what kind of algorithms or operations do we learn for them? Mhm.
Can you repeat that, Professor? You kind of cut off.
Oh, I was okay. Cut off. So my question is that so what kind of algorithms did we learn for stack and queue? Or operations?
Insert and deletion.
Yes, great. So see, that structure is basically a place for a container for us to store the data, whereas algorithm is the operations over the data that we store in the container. So for stack and queue, we learn some functions like, or algorithms like insertion, deletion, and then we learned another data structure, let's say binary search tree. So what kind of operations or algorithms did we learn over this data structure? What kind of operations did we learn for binary search tree? Can you hear me?
Yeah.
Okay. So we basically learned traverse algorithms, like in order. Traverse algorithms in order, post order, and then we learned the most important function for algorithm named search. And also we learned something like insertion, deletion, and how to find the minimum and maximum. Okay, so that is for binary search tree. And so today we're going to learn another data structure named the graph. And so for graph, there are a lot of algorithms associated with it. Most of them are regarding search. And in total, we're going to learn 11 search algorithms in graph, okay? Search algorithms in graph. And that is this 11 search algorithms is going to be our focus. So in the following 4 weeks. Okay, so first, let's look at what is a graph. So a graph is basically a set of nodes that are connected by a set of edges. So that's why, so we denote the set of nodes as capital V, and we denote the set of edges as capital E. So V means vertex, okay, the set of vertices. So basically, we represent in the mathematical way, we represent a graph G as a combination of V and E, a set of nodes and a set of edges. So here from the definition of the graph, some of you may think, okay, it's more. So previously we also learned some data structures that are very close to this one. For that is tree, okay? So if we talk about tree, yes, this is a tree, okay? In the tree structure, we also have a set of tree nodes that are connected by the edges or links. So, but there is a big, so trees is more like a special, a particular type of graph where we put the nodes in a hierarchy with different levels. Okay, so and also each node can only have one parent. So going onward, each node can have at most one link. Okay, so this is the limitation of tree, but a graph is more like, so we got a lot of freedom in graph, so we can, there is no hierarchy, so we can put the nodes, so connect the nodes any way that we want. So this is the difference between graph and tree. So here is one example of the graph. So here you can see that we have, in this graph, we have 5 nodes that are connected by, say there's 7 links, or yes, 7 edges. And also here is another graph. So in which we got 6 nodes and a set of edges. But here, do you see the difference between these 2 graphs? What is the biggest difference between these 2 graphs?
The
A
first one is
recursion?
all connected.
Yes, cool. So yes, the biggest difference is that in the first graph, the edges are not associated with a direction, whereas in the second graph, the edges come with a direction. So here we say we got the edge from node 1 to node 2, but there is no edge from node 2 to node 1.
Wait, Professor, does that mean like 6 is isolated by itself?
6, yes, you can take it that way. So we can go from 3 to 6, but from 6 we cannot go anywhere, right?
Yeah.
Yes, we will learn how to discover these isolated nodes later, next week. Okay, cool. So yeah, great. But the biggest difference between these two graphs are that in the first graph the edges are undirected, whereas in the second graph the edges are directed. So based on the fact if the edges have an direction or not, we have two types of graphs. The first one is called undirected graph, whereas the second one is called directed graph. Okay, so can you think about anything? Let's say, can you come up with any application where we need to use undirected graph?
I think if you're trying to find the fastest route to probably 2 different nodes.
Mm-hmm. Cool. I mean, so what we are talking about is that the so if we want to find the shortest distance or the fastest route between two places, then we should use a graph to model the structure that we have and perform a search over it, right? Yes, that's cool. Yes, and so to put it in a more concrete way, we can take it as this. Okay, this is the cities in the United States, different cities in the United States based on the population, and here, so we definitely know that these cities are connected by roads. So what we can do is that, so suppose here is one city. Let's say this is Seattle. And this is LA, and we have some other places like St. Louis, and also we got Philadelphia and in New York. So so suppose here we're just considering these 5 cities, and if there is a highway, a direct highway that connects 2 cities, we build an edge between them. Okay, so let's say from Seattle there is a road to go to St. Louis, and then from St. Louis there is a way to the direct highway that connects with NYC, and then okay, so here we basically can model the road network in a country by using a graph where the nodes denotes different locations and the edges denote the roads.
Professor, I have a question.
Sure.
We can do this with directed graph, right?
With directed graph?
I mean, yeah, since they like kind of only go one way. That's what I'm seeing from the image.
Okay, so here there is no need, in this example, there is no need for us to model it with a directed graph, because usually when we build roads, if you build a road that goes in the north, let's say if you build a road from LA to Seattle, definitely you will build a road in another direction, that is to go from Seattle to LA, right?
Mm-hmm.
So it's like so then there is no need for us to associate a direction with the edges here. because like if it's basically mutual. If you can go from A to B, definitely you can go from B to A.
Yeah, okay, I got it.
Okay.
Thanks.
But that's a very good question. Okay, so this is one famous application of the graph. And the other thing that we can come up with is social network. So suppose here we're considering Facebook. And so suppose here, this is my account, and then this is your account, and this is my friend's account, even though I don't have the app on my phone and I rarely use that. I rarely log into that. So suppose that you send me a friendship invitation, say, okay, Professor, I want to be a friend with you. If I accept your invitation, then we become friends. So then Facebook is going to the way that Facebook models the social network is to create an undirected graph. So suppose this is my parent. Okay, so this is a typical network. So suppose that this is you and your friend. So this is how how Facebook so maintains the account and the friendships. So okay, and so he can come up with a different social network platform where we need to use directed graph rather than undirected graph. Is there a social network where we should use directed graph? We have to use directed graph.
Maybe in a video game?
Say it?
Said maybe in a video game?
Video game? I'm talking about social networks.
Oh, well, there's
LinkedIn.
LinkedIn. So I think it can be undirected, because if you send a friendship invitation with me, or if you ask me to build a connection, if I agree, then I will be in your network, and also you will be in my network. So the friendship is mutual.
Okay.
Right? So there is no need to use directed graph.
What about like TikTok? Something like TikTok.
I never use that application. I'm not sure.
It's almost like Instagram. Like you have to follow the person to see.
Okay, followship. Okay, yes. Even though I never use Instagram, but if you talk about the followship, I think I do use Twitter sometimes, but let me use Twitter as one example. Okay, suppose this is your account, and this is the president account. Now it is Joe Biden, and so so definitely you want to, if you follow Joe Biden. So here we create an edge from you to Joe Biden, meaning that you are following Joe Biden. That is it necessary for Joe Biden to follow you back?
No, it's not necessary.
No, right. So in this case, we should use directed graph, because if we don't associate this with the directed graph and we just use it an undirected edge to link these two nodes, you don't know if who is following who. But here, because it is you who follows Joe Biden, so we need to create an edge from you to Joe Biden. Okay, so so basically, if the relationship between two nodes are mutual, then so we need to use undirected graph. Whereas if the relationship is not mutual, we should use directed graph. Is that clear?
Yes.
Yes.
Okay, so put on the code. So okay, so that I can see. Okay, so so this is the application of graphs, and also so this is a mathematical question. Okay, suppose here, if we are giving a graph with a set of nodes and a set of edges. So how many edges can we have at most? What is the maximum amount of edges?
Is it V, the amount of nodes?
V, definitely more than V. So for example, let's come back here. In this graph, how many nodes do we have?
5.
5, but we have 7 edges,
Oh yeah.
right?
Correct.
So it's more than V. Okay, let's say this. Okay, suppose here we have in our class there are 20 students. There are 20 students. So if any two students, student A and student B, so they like each other, they will be friends. They will be friends. So basically, my question is that how many pairs of friends can we have at most if there are 20 students in our class? What is the maximum amount of pairs of friends?
Are the pairs mutually exclusive? Can like A be friends with B and C?
No, no, I'm just talking about any 2 person. I'm not talking about 3.
If there's 20 students and 10 pairs, but
No, more than that. Because if student A is, if A is a friend with B, A can also be a friend with C.
Mhm.
It's not mutual, so it's not mutually exclusive. It's not like getting married. So so if you get married to someone to A, you cannot get married to B. But if you here we're talking about friends. So if you are a friend of A, you can also be a friend of B. Say it. Can you say it again?
that wasn't me. I think someone just has his mic off.
Okay. So, and any idea what is the maximum number of pairs of friends?
I would guess it's like squared.
In square, yes, great. Okay, the thing is that, so here let's first talk about the friends thing. Okay, so the maximum number of friends is this, pairs of friends is 20 times 19. So the reason is that for student A, this student can be friends with at most 19 other friends, right? 1, 2, 3, 19. So in the best case, this student makes friends with all the other people. So he has 19 friends. Then student B also has 19 friends. Student C also has 19 friends. So we just sum them up. So in total, at most, we have 20 times 19 pairs of friends. Make sense?
Yeah, now I get it. I
Okay.
wrote 20 times 20. Well, then now I understand 19 because you can't be friends with yourself.
Right, right. So here in this example, you can't be friend with yourself. So it's like 20 times 19, or say if we want to be general, we're not talking about 20, we're talking about n friends. Then we got n times n minus 1 friends at most. Okay, so in terms of the graph, so it's like we have V nodes. How many pairs of edges can we have? Similar to here. Okay, in the worst, in the best case, we have say for each node, this is node X. It is the it has a link with an edge with all the other nodes. Plus, because we're talking about a graph, this node can have an edge with itself. It can have an edge with itself. So in total, for this node X, you can have at most V edges. Correct?
Yeah.
Yes.
Yeah, so they can have an edge with all the other nodes and also with itself. So in total, we have at most V edges. So for all the nodes, this is, let's say this is not X, this is V1, the first node V1, V2 until Vn. For every node, the maximum amount of edges is V. So we just sum them up and then we got a V square. Make sense?
Yes, that makes sense.
Okay, cool. So this is just a mathematical thing. Okay. So and the next question is that how are we going to represent a graph that's structured by using a computer program? So so the first way is called an adjacency list. So suppose that we have a graph like this. Then the idea is that for each node, we're going to create a linked list of its neighbors. So for example, here, what are the neighbors of 1?
2 and 5.
2 and 5. So for node 1, we create a linked list that includes 2 and 5. So let's say, what are the neighbors of 2 of the node 2?
Is it
1, 5, 3, 4.
Yeah.
1, 5, 3, 4, all of them. So then for the node 2, we create a linked list that includes 1, 5, 3, 4. You got it?
Yes.
Yeah.
Yes. So basically for each node, we create a linked list that stores all of its neighbors. Okay. So that is one way, but to create, so to do that, we have to manually create the linked list, and it's going to be time consuming. So to make the things simple, people propose another way that is called adjacency matrix, and this way is more popular. So the idea is that, so if we are giving a node that includes if we are giving a graph that includes 5 nodes, then we're going to create a 5 by 5 matrix. And here, each row and each column basically represents a certain node in the graph. So suppose here we have an edge that connects 1 and 2. There is an edge between the node 1 and node 2. Then we're going to set this one. So this place 1 and 2 as 1. Okay, so basically, if there is an edge, going from node I to node J, we're going to set the corresponding style of the matrix as 1. Otherwise, it is 0. So basically, 0 means no edge between these two nodes, and 1 means there is an edge. So for example, here, let's say for the node 1, okay, its neighbors are 2 and 5. So we set 1, 2 as 1 and 1, 5 as 1. A1, 2 equal to 1 and A1, 5 equal to 1. Okay, and so here let's talk about node 2. Okay, so its neighbors, it has an edge to node 1, 5, 4, and 3. So we're going to set A2 1 as 1, A2 3 as 1, A2 4 as 1, and A2 5 as 1. Okay, that is what we do in the second row. Okay, we set all the cells to 1 except for 2 itself. Okay, make sense?
Yes.
Yes.
Okay, and here if we're giving okay, before that, let's say if I ask you to fold this adjacency matrix along this line, along this diagonal. So what are we going to observe? If I ask you to fold it in this way, what are we going to observe?
Is it that the diagonals are symmetrical?
Yes, it is symmetrical along the diagonal line. So it's going to be exactly the same after we fold them. So is this by some luck, or does it has to be this way?
It's by design.
Yes, it has to be this way because this is an undirected graph. In an undirected graph, if we have an edge between I and j, it means that from I it's in an undirected graph. So an edge actually means an undirected edge actually means two directed edges. It's more like this way. The relationship is mutual. Okay, so then we need to set both Aij as 1 and also Aji as 1. That's why we got the symmetric adjacency matrix. Make sense?
Yes.
Yes,
Does,
makes
yeah.
Okay,
Yes.
cool. And so, but if we're giving an undirected graph, then so here you can say that if we fold it along this line, we basically build the adjacency matrix in the same way, but if we fold it along the diagonal, it's not symmetric anymore, right? Only the adjacency matrix of a undirected graph, so has to be symmetric. Okay, so here so then I have one question. Okay, if you are giving such an adjacency matrix, and if I ask you to find the neighbors of node 3, what are you going to do? So now you don't look. I don't allow you to look at this graph anymore. By just focusing on this adjacency matrix, how are you going to find the neighbors of the node 3?
You either look at the row of row 3 or column of row 3.
You look at the row. So if there is so let's use this as an example. Okay, so in this example, okay, what are the neighbors of node 3?
5 and 6.
5 and 6. So if you go to the row 3, you will see, okay, only 5 and 6 have a 1. It means that there is an edge that goes from 3 to 5, and there is an edge that goes from 3 to 6. So the neighbors of 3 is 5 and 6. Make sense?
Yes, but you could also look at the columns as well,
No,
right? It
no.
doesn't-
For directed graph, you can. So here, let's say if you look at the column, if you look at this column, all zeros.
You're completely correct. Yeah, my bad.
No problem. So the reason is that when we're talking about neighbors, we're talking about from the neighbors of some node. Let's say the neighbors of 3. We're talking about, okay, which node can you go directly from 3 to? Okay. So then so we're talking about from 3, which node can you go to directly? So then we need to look at the third row, not the third column. If we're talking about which nodes have an direction, have a link to 3, then you should look at the column. Otherwise, you look at the row.
So the column shows what is connected to that node,
Yes.
and the rows show what
What-
that node is connected to.
Connected to, yes.
Okay.
Okay. So in your homework, you will need to be able to find the neighbors of a node, like by going to the row and find the index of ones. So you will be able to find the neighbors of a certain node. Okay. So far I finished introducing the definition of of graph, and as well as how to represent it by using a computer program. And most of the time we use this way. We use the adjacency matrix way. And we're going to stick to this convention in our homeworks. Okay, so now do we have any questions?
Good so far.
Okay, cool. So then let's learn the first algorithm with the graph that structure. So the first algorithm is named breadth first search. So its input is a graph as well as a source node S. So this is a node. S is a part of V, the set of nodes. So it's just one node of the graph. And the output we want the output to be the shortest. So the shortest distance from the source node to every other node. We want to learn, okay, from this source node, what is the shortest distance from the source node to every other node. So here, if we take this graph as an example, okay, so if this is a graph, and if we take this node, the Frankfurt, as the source node, so basically we want and if we run this search algorithm against this graph and this source node, it is able to tell us what is the shortest distance from Frankfurt to every other node in the graph. So for example, if we look at this node, this node, Munich. If we look at this node, Munich, so from Frankfurt, how many possible ways do we have to go to Munich? This is one way.
Oh,
okay, so yes, I heard 3. Yes, I think it's correct. And this is another way. And this is another way, correct?
right.
Okay, so here, let's calculate the distance. So for the green one, let's say the distance is 85 plus 80 plus 250 plus 84. Let me say it is 494. No, 499. It is 499. And how about the green? How about the blue one? So it is 217 plus 103 plus 163. So this is 487. Okay, this is 487. What about the pink one? This is easier. Okay, 173 plus 402. This is 675. So if we run this algorithm against this input, then it will tell us, okay, to go from Frankfurt to Munich. So the minimum distance is 487, and you need to use this route. Okay, so it will be able to tell us the shortest distance from Frankfurt to every other place in the graph. Okay, so any question with regard to the definition of the breadth first search algorithm? Are we good so far?
I'm good.
Yes.
Okay, cool.
I'm good.
So then let's look at the pseudocode of the breadth first search algorithm. Takes 2 inputs, the graph G and the source node S. For each vertex U, so what does this mean? What does this operator mean?
Element of. U is an element of G.
Yes,
dot
an
B.
element of belongs to or belongs to. So basically, so it means that if we're talking about this, okay, so if say 5 is an element of a set with 1, 2, 3, 4, 5, then we say this is true, right? But if we ask, okay, if 5 belongs to 1, 2, 3, then this is false, correct?
Correct.
Yes.
So this is basically the element of operator, okay? Okay, so and then, so here we have G dot V. For each U, vertex U belongs to G dot V minus S. So it's like for if this node U is a node in the graph except for the source node, okay? So then we associate it with a color, a white color, and an infinity D and a pi that is nil. And then we associate the a gray color with the source node. We associate a 0 D. We associate it with a neo pi. So here, what does color D and pi stand for? Okay, so here is the explanation. So D means the so for each node V, for any node V, V dot D means the minimum distance from the source to it, from the source node to it. Okay, so it means the minimum distance between the source and V. And pi so means the parent of V to reach S. So let's say, okay, let me use this as an example. So this is the shortest route from Frankfurt to Munich, correct?
Yes.
Okay, so then in that way, we say the parent of Munich is Newburgh. Is Newburgh because to reach if we follow the shortest route, then the last node before Munich is Newburgh. So we say Newburgh is the parent of Munich. Okay, so here parent means what is in the shortest route, what is the last node you need to visit before V. Okay, best you can, for now you can take it as the parent. It will be very clear in maybe 30 minutes. Okay, and V dot color. So we also associate each node with a color. The color can be either white or gray or black. So so white means, so if a node has a white color, it means that we haven't visited this node before. And gray means that we have visited this node, but not its neighbors. So if a node is in black color, then it means that we finish visiting both this node and all of its neighbors. And we will not visit this node again in order to save the time. Okay, so this is the color. So what does the color mean? And then let's go. So in line 8, we have Q equal to this. What does this mean?
Q equals to null.
No, not now. Not now. If we use neo to represent now. What does this mean? An empty site.
I see.
Okay, so here, okay, let's just continue and say, let's say we say in Q, QS, and then we say DQ. So if we use in Q and DQ, what kind of things can you remember? So what does it remind you of?
The binary search tree.
No. In binary search tree, we don't learn the function like InQ, called InQ or DQ. We only learn search, minimum, a maximum, and we also learn something like the successor.
I saw it in one of the homeworks. I'm trying to remember. I knew I saw it somewhere.
Yeah, definitely. Yeah, it's Q, right? InQ is to insert an element into the queue, and DQ is to remove an element from the queue, correct? Okay, cool. So here you can say that because this queue, this capital means that we're going to create a queue. And this initially this queue is empty. It's like we create a queue with nothing stored in it. Okay, so and then next we are going to include the source node into the queue. And while queue is not this, while queue is not empty, so while the queue is not empty, we dequeue, and then for each v that belongs to the g.adju. What does g.adju mean?
Is it the array of the?
No, it means the neighbors. This is a function. It means the neighbors of u. For each node v, that is a neighbor of u. Adj is short for adjacent. For each node v that is a neighbor of u, if the color of v is white, then we do something and we include it. So after we finish the for loop, we assign a black color to u. Okay.
The program isn't done until everything is black.
At the end of the program, everything is going to be black, and the queue is going to be empty.
Perfect. Okay, thank you.
Okay. So this is the algorithm, and I'm going to use an example to explain it. Okay, so BFS for each node u belongs to g.b minus s. We have u dot color u dot t equal to infinity, and u dot pi is nil, and s dot color goes to gray, s dot t is 0, and s dot pi is nil. And then we create q as empty, and then we have in q Okay, so this is the first part of the pseudocode, and I'm going to use an example over here. Okay, so this is how the graph looks like. Okay, so okay, before I explain the pseudocode, I need to mention one thing, because in the next couple of like 20 minutes, I'm going to use these three colors: white, gray, and black. And as you know that at this time, I think colors are kind of like sensitive. So I'm not a racist at all, so I don't want to offend anyone, but I'm just following the convention of the pseudocode to use white color to denote something, gray to denote something, and black to denote something. Okay, so yes, just to play it safe. I mean, if you are sensitive about it, I mean, I don't mean anything. Okay, and personally, I think it's not a good idea. Definitely, it's not a good idea to relate everything to color or race. So if people relate everything to it, if someone relates everything to race or color, that person by itself, by him or herself is a racist. I think the best way to respect different people of different races is to ignore the race. You just take that person as a person without color. So that's how I deal with it in my life, and I don't. So currently, I say a lot of things are related to that. Yeah, definitely things come with a reason, with especially a political reason. But I personally don't like it. Okay, even though I'm a people with color, I'm a person with color, and I'm also a minority. So I don't like that. Sure. Let's come back to, let's forget about politics and talk about the algorithm. Okay, suppose here we're giving such a graph, and we want to perform the breadth first search on it, and let's say we have this node as the source node. We take B as the source node. This is our source node. Okay, so we have S equal to B here. We have S equal to B. So B is the source node. We want to discover the minimum distance from this node to every other node in the graph. So first, for U belongs to G dot V minus S. What is G dot V? So what is G dot V? What does G dot V denote? It denotes the set of nodes inside the graph, correct? Can you hear me?
Yes.
Okay, so so what are the set of nodes? What is the set of nodes inside the graph? A, B, C, D, E, F, G, H, correct? Okay, so yes, this is the set of nodes. So basically we're going to use this minus the source node S. Here we have S as B, so we replace this with B. And the result of it is basically A, C, D, E, F, G, H. Okay, so C, D, E, F, G, H. Okay, so this is the list of nodes that we're going to go over. So for U belongs to this set. So initially we have U as we have U as the first node A. So we have U over here. We're going to give associate U with a white color and an infinity distance and a neo parent. So for this node, we're going to give it a white color and infinity distance and neo color. Neo parent. And then so far we just finished A, and then we move U to the second node, which is C. Okay, so then we associate with a white color, infinity distance, and a neo parent. So this is what we do with this node. Also next we move to D. Okay, so we do the same thing, white color and also for EFGH. So we're going to do the same thing. Okay, so this is the result after we finish the first for loop. And the next we have s.color as gray. So this is the s. So we give it a gray color, and then we give it a 0 distance, and then we give it a neo parent. Okay. So and then so before I proceed, I'm going to ask you, why do we associate a 0 distance for the source node for S?
Professor, can you repeat that, please?
Okay, so my question is that why do we associate, why do we assign a 0 distance to S to the source node? Yes, great. Yes, I see the answer immediately from the chat area. That's brilliant. Okay, so let me put it this way. What is the minimum distance from your home to your home?
0, you're already there.
Yes. So here, because our objective is to find the minimum distance from S to all the nodes in the graph. So the minimum distance from the source node to itself, it has to be 0. Great. Excellent. Okay. So here we give the gray color to denote it's if you remember, a white color meaning that the node has not been discovered yet. Gray means we have discovered the node but not its neighbors. So we give it the source node a gray color, meaning that it's like we're standing at the source node, and now we're going to explore the other nodes in the graph. So that's why we assign a gray color to it, but assign a white color to all the other nodes. Okay. So next we are going to create a queue, an empty queue. So I'm going to list the empty queue over here. Which is initially empty. And next we're going to enqueue it. We're going to enqueue S to the node. So we have the first node in the queue now, so which is the source node, and it is B, correct?
Yes.
Okay, cool. So yes, it has one node B. Okay, so far we finished the first part of the pseudocode. Any question for me? Are we all good so far? Okay, so then I'm going to continue. Well, Q is not empty, and we have U equal to DQ. And so for each V that is adjacent to U, if V dot color equal to white, and then what we do, we have V dot color as gray, and V dot D equal to U dot D plus 1, and V dot pi as U, and also we enqueue and then at last we have U dot color as black. Okay, so this is the second part of the pseudocode. So next, let's say okay, while Q is not empty, so is the Q empty or not? So is this queue empty or not?
No.
No, it's not empty. So we are able to proceed. So first we dequeue. So which element are we going to get out from the queue?
Is it B?
Yes. Now we only have one element in the queue. So B is going to be eliminated. And so we have this, we have, let's say we have Q as B. Okay. For each V that is adjacent to U, what are the neighbors of B?
Neighbors would be F and A.
Yes, A and F. Okay, so first we have V as the first node, first neighbor, A. Let's say V is here, V is here. And so what we do is that first we check the color of V. So is the color, is it color white, or is this true? Does it have a white color?
Is it a known for now?
Sorry?
Is it white for now?
Yes, it's white. W means, so here W is in short for white.
Hmm.
G is in short for gray, and B is in short for black. Okay, so now it is white. So this is true. And then we're able to continue. So we assigned a new color, gray. Okay, so we give it a new color, gray. And next, we set its distance, v dot d equal to u dot d plus 1. So sorry, this is u, and also this is u. This is u. Okay, what is u dot d?
The distance
0.
from, yeah, 0.
U dot d is 0. So this is 0 plus 1 is 1. So we give it we assign 1 as its distance. And then we assign, next we assign u as its parent. So u is b. So here we're going to change it to be something like this. We change all of its colors and its distance and its parent. Okay, and next we're going to enqueue it. We're going to put this node V into the queue. So this node V is A, so we have the queue includes a node A. Okay, so then we finish one iteration of the for loop. Next, we're going to have another iteration of the for loop. We have V as F. So V is over here. And then we're going to check if color is white or not. Is it true?
Yes, it is white.
Yes. Okay, this color is white, so we're able to continue. So we can say give assign a new color gray, and so assign a new distance to it, which is u dot d plus 1, the same as what we did for the node A, and give it a new parent, which is u. So the same as what we do for the node A. So now we're going to give it a gray color and distance 1, and we're going to set its parent as B, and then we're going to enqueue it. So F is also going to the queue. Okay, so then we finish the second iteration of the for loop. So now we finish the for loop, and then we're able to execute the last line. In the last line, we change the color of U to black. So here, this is U, so we change its color to black. The reason for us to change its color to black is because we finish visiting this node plus all of its neighbors, A and V. So according to the definition, okay, if we finish visiting a node and all of its neighbors, we are going to give it a black color. Make sense?
Yes.
Okay. So after this line, where should we go?
Do we go back to the for loop?
No, we go back to the while loop.
Okay.
So this is a part of the while loop, not a part of the for loop. So we go back to the while loop and we check if the queue is empty or not. Obviously, it's not empty. So we're going to call the dequeue function. So which node are we going to dequeue now?
Is it A?
Is it A? Good question. So what kind of policy does queue enforce? Last in, first out, or first in, first out?
I'm not sure. I don't recall.
It's the queue, so it's first in, first out.
Yes, first in, first out. So among these two nodes, A comes into the enters the queue first. So we're going to eliminate A first. Okay, so we dequeue A, we remove A from it, and so this is going to be A is going to be the node U. Okay, and what are the neighbors of A?
E and B.
E and B. Okay, so let's start with the oops, I used the wrong thing. Okay, G.ADJU. Okay, so first we start V as E. So this is E. So V is here, and let's check if the color of V is white. Is this true?
Yes, it is white.
Yes, this is white. So we are able to continue. So we're going to execute the next 4 lines with v.color equal to gray. So we change its color to gray. And also we are going to set its distance as u.d plus 1. Okay, this is u. What is u.d? What is u.d?
The distance itself, u.d.
Is 1.
Yeah, 1.
1. So 1 plus 1 is 2. So we're going to assign distance 2 to it. And then we're going to assign a parent to it, which is u. So u is A. So we are going to assign its parent as A. And next we're going to enqueue it. Okay. So put this node V, append this V at the end of the queue. So we have we append this node V, which is E, to the queue. Okay. So this is what so then we finish the first iteration. And then next we start another iteration with V as B. Okay. So what is the color of B?
Black.
So this is
False.
false. So we're not going to do anything with it. We're not going to do, so this is false. So we're not going to do anything with this. So we just skip this iteration. So here you can see that for any neighbors of U, if its color is not white, we're not going to do anything. We're going to leave it alone. So this is what we do over here. And then we finish the for loop. We go to the last line by assigning a black color to the node U. So the node U now so it has a black color. This is because we finish visiting this node as well all of its neighbors. Okay, so so we finish this iteration of the while loop, and then we're going back to the while loop. So is the queue empty or not?
It's not empty. We have F and E.
Yes. So then we're going to dequeue. So which node are we going to eliminate from the queue?
F.
Yes, because F enters the queue first. So F is going to be eliminated. We have U as F. So let me put U at F. This is U, okay? So then what are the neighbors of F?
B, C, and G? I can't see that very well, but I think it's G.
Yes, BCG. So so its neighbors are BCG. Let me get my shoulder. So so the neighbors of U is basically BCG, and so previously we said that if for any obvious neighbor, if is so we're only going to execute these 4 lines if the neighbor has a white color. So here among BCG, we say okay, B's color is black, and while the other 2 nodes have a white color, so we can leave B alone. So we can just totally ignore B, and then so only do the work for C and G. So first we have V as C. So we put V over here, and so we're going to say okay to execute the 4 lines. So we're going to give it a gray color, and we're going to set its distance as U dot D plus 1. So this is U. What is U dot D?
One.
Yes. So 1 plus 1 is 2. So we're going to give it a distance 2, and we're going to set its parent, V's parent as U, which is F. So it becomes G2 and F, and then we're going to include it. So we put C at the end of the queue. And next, so we finish the iteration at C. Next, we're going to start another iteration at G. We're going to do the same thing for G. So we're going to give it a gray color and change its distance to 2 and make it parent F. And also we're going to include it. Okay, so then we finish the iteration at G, and then we're going to finish the whole for loop, and we're going to execute the last line with U dot color equal to black. So this is U, so we're going to change its color to black. Okay, so then we go back to the while loop. The queue is not empty. We still have 3 nodes in the queue. So then we're going to dequeue again. So the node that we're going to dequeue is
E.
Okay. So we have U as E. Let me write it in a clear way. So U is E. Let me say yes, this is U. What are the neighbors of E?
Just say
Just A, but its color is already black. So we're not going to do anything for it. So we can just totally ignore it. And then we finish the for loop, and we simply go to the last line and assign U a black color. Okay, so this is what we do in this situation. Next, we go back to the while loop. It's not empty, so we dequeue. This time we're going to dequeue C, yes. So we have U over here. What are the neighbors of C?
F,
G.
and D.
H. Oh, sorry. Yes, just FGD. FGD. No H. F, G, and D. So among them, whose color is white?
F is black, G is gray, and D is white.
So we're only going to do some work for D, right?
Yes.
Yes.
Okay. So first, so we are going to have V as D. So we're going to do this, change its color to gray, and set its distance as U dot D plus 1. Here, U, this is U dot D is 2. So 2 plus 1 is 3. And we're going to assign U as its parent. U is C, so its parent is C. And then we're going to include it. So sorry, so I should have eliminated C. Okay, so we're going to include it. So D is in the queue. And then we finish the whole for loop. So then we go to the last line and assign U a black color. Okay, so next we go back to the while loop. So it's not empty, we're going to dequeue. So which node are we going to get?
G.
G is gone. We have U as G. Okay. So what are the neighbors of G?
F, C, D, H.
F, C, D, H. So, but among them, only H has a white color, correct?
Yes.
So we're only going to work on H, and so what we do is that we are going to set its color to gray, and give it assign its distance as u dot d plus 1. So here u dot d, this is u dot d is 2. So 2 plus 1 is 3. And we're going to set its parent as u, which is G. So okay. And then we're going to include it. Okay. So then we finish this for loop, and then we're going to the last line and assign G a black color. Okay, so next, so we go back to the while loop, and we're going to DQ. So the node that we remove is D. So does D have any neighbor whose color is white?
No.
No.
No. So its neighbors include C, G, H, but none of them is white. So we're not going to do anything in the for loop part. So we directly go to the last line and assign a black color. And then we go back to the while loop again. The queue is not empty, so we are going to DQ. So H is going to be removed, and we have U as H. Okay, so does H have any neighbor whose color is white?
No.
No, so we're not going to do anything. Instead, we go to the last line and give it a black color. Okay, so then we go back to the while loop, but now the queue is empty. So we cannot proceed the while loop. So we terminate, and then that's the end of the function. Okay, so just type in 1 if you follow me through all the process and you understand it. Okay, I see around 10 ones. Okay, that's fantastic. And so here, remind me, what is the objective? What is the expected output of BFS? The minimum distance from the source to all the nodes, correct? Correct? So here, let me say, what is the, so you may ask, okay, what is the minimum distance from the source node here to H? It's here, 3. So some of you may ask, okay, what is the shortest route that gives us the distance, minimum distance 3? You only need to follow the parent. So the parent of H is, what is the parent of H? It's G. Okay, so it means that in the shortest route before H, you should visit G first. And then what is the parent of G?
F.
Yes. So in the shortest route before G, you should reach F. What is the parent of F?
B.
B.
Oh, I see. So the shortest
So-
part is
Yes. And then the parent of B is nil. So it means it's the beginning of the route. So this is the shortest route that gives you the minimum distance 3.
I have a question. What's the minimum distance from E to H?
From E to H, we don't know because the source node is B. So what we discover, we only discover the minimum distance from the source node to every other node. Here you're asking for the minimum distance between E and H. None of them is the source node, so we don't know.
I see. Thank you.
No problem. Okay, so let's use another example. So let's say we want to find the minimum distance from the source node to E. Okay, so here the minimum distance is just 2. So the shortest path is that from E, before E we should go to its parent, which is A, and before A we should go to B. Over here, B's parent is neo. So okay, then this is the shortest route that gives us the minimum distance 2. Make sense?
Yes, it makes sense.
Yes, it does.
Okay, so any question for me? No?
What would be the time complexity
Oh,
of
nice.
BFS?
Cool. Yes, that's what I want to discuss. The time complexity is V plus E, the number of nodes plus number of edges, because we basically here we are using the color. The reason why we associate each node with a color is to avoid repeatedly visiting the same node multiple times. So as you can see that we only visit a node if its color is white. If its color is white, meaning this node has not been discovered yet. So with the color assigned, with the help of the colors assigned, we are able to limit the visit to each node at once, exactly once. So that's why we got the V plus E complexity. Make sense?
Yes, that makes sense.
Yes, it does.
Okay, so then this is the breadth first search algorithm, and so I finished discuss it and finish the discussion of that, and so let's go to the next one called DFS. But before that, so I want to discuss one thing. So I'm not sure if you remember that in one lecture I asked you, what is the value of $20,000? Do you remember that?
I do.
Okay, so in that lecture we discussed quite a few say investment options, and for example education, stock, and real estate, and also something like buying a car. And so I in that lecture I said that if you invest on stock, so typically the typical rate, what is the typical return rate of a stock, annual return rate?
You said 8% was the typical, but you were making 11.
Yes, I was able to make around 11 to 12%, anywhere from 11 to 12%. So after I stated that, I received 3 emails asking me, what is the portfolio to give me 11 to 12%? Okay, so it seems that some students are really interested in learning how to invest. That's good. So I wish that I could learn it at your age. I'm not going to show you my portfolio because different people, each person has a different so tolerance of risk. Because if you want to go for more return, higher return, it usually means higher risk. So but so the thing is that, okay, if you are not going to use your money, if you don't need for any money that you don't need in 10 years, so basically you have to invest your, if you don't need that money in 10 years, and you can invest it in a high risk stock, like what I did. and which gives you a very good return rate. And so if you don't need, but be prepared for 10 years. So it's like leave it alone for 10 years, and so that you will be able to pick up after 10 years or longer time, you will be able to pick up a much bigger cake. So the on average, okay, so here I'm just going to give you a couple of suggestions on how to pick the fund. So first, number one, don't pick a single stock because it's too risky. So for example, if you invest on Ford 20 years ago or 10 years ago, it's that at that time for Ford each stock is worth around $120, and now it's only worth $30. So your investment rate, your return rate in 10 years is like negative 75%. That's too risky. So you only pick fund. You only invest on fund, which is a combination of hundreds of stocks, and it reduces your risk. So okay, so if you want to learn how to invest that, okay, pick some fund in different categories: small growth, medium growth, and large growth, and international growth. Okay, you pick the fund that has a big potential to grow. Okay, so so that's how you do that. How I got my annual rate around 11 to 12%, and previously you probably see the power of this 11 to 12% against 8%. It's say in $20,000 if you leave it there for 50 years. If you get 8% return, so you will end up with a little bit less than $1 million. But if you invest on this, you will end up with a little bit over $3 billion. Sorry, $3 million. So there is a big difference between them. So that's my advice, and also a very good thing for you because you are really young, and you can just go for something which gives you a tax advantage. Is there anyone who heard about something called Roth IRA? Anyone heard about this one?
I have no idea what it is.
Isn't that like a
Okay.
retirement account?
Yes, it's a retirement account, but so usually say if you
It's not
invest
taxed,
on,
right?
yes, if you invest on a stock or fund, at the time when you collect your, so suppose you buy a stock today and then in 1 year you sell it, right? At the time when you sell it, suppose that I say you make $100 from the stock, you're going to pay $45 as the tax. Okay, you need to pay $45 as the tax. So you only end up with $55 in your pocket, and the 45 goes to the federal government. So the beauty of Roth IRA is that whatever you earn from your investment is tax free. Okay, so if you make $3 million, if you make $3 million, from that, from your $20,000, actually you make, so your return is $280,000. All of this $280 is going to go into your pocket, become your retirement fund. So if you don't do Roth, you directly go for say an ordinary retirement account. Then, so out of this you only end up with say from 0.5. Let me say how much is that. So you only end up with 1.5, so $154,000 in your pocket. So over 1 million goes to the federal government. So this is a very, very good retirement way. Okay, so if you don't have a Roth IRA account yet, open up one. You can open it up at either Vanguard or Charlie Schwab. Personally, I recommend Vanguard because it has a lot of funds for to pick. So if you don't have that yet, go for it now. Okay, so as long as you have you have your W2 or you make some income, you can invest on your Roth IRA, and each year you can invest up to $6,000. So that's the limit for now. Okay.
What was the first one again? How do you pronounce that?
Vanguard.
Vanguard.
Yes, VANGUARD.
I actually have a friend who works at Charles Schwab.
Charles Schwab is also okay, but Charles Schwab does not have a good selection of funds. So anyway, any of Charles Schwab or Vanguard is fine, but I personally prefer Vanguard. I transferred all my portfolio from Charles Schwab to Vanguard maybe half a year ago. So because I found it's better. It's hard to explain why it's better, but in general it's just better. So okay, go for it. And guys, just do this as early as possible, because if you invest it now, it has more time to grow tax-free. So that's my advice. I lose 10 years of investment, and that is very valuable. So I have to make it up now. So since you are young, be prepared for that. And actually, another question that I have for you is that how much is your car payment each month? How much money do you pay for your car, either lease or say finance?
500, 600.
500, 600. Okay. So do you know? So what is the average car payment for Americans is $440. Okay. So if you don't invest that on cars, instead you invest it on the Roth. Remember, you only have a 6,000 limit every year. So which means that you can only invest $500 per month. Okay. So which is exactly almost the same as the car payment for an average American person. Okay, if you keep doing that, if you keep investing $500 a month to your Roth, and if you keep doing that from your age 20 to 60, do you know how much are you going to? Just let's say you only make 8%. You just leave it. So you don't do any research. You just leave it invest on SP 500, a no-brain investment. Do you know how much are you going to have at age 60?
You showed us the calculations on a website that you programmed.
Yes.
I think it was like around 2 million or something.
So if you keep doing that, so that is 50 years. Now it's only 40 years. Okay, it's only 40 years and 80%. How much? You end up with exactly $1 million in your retirement account. Okay, so which is totally tax-free. So, I mean, what I say is that, in my neighborhood, a lot of people, senior people, like in their age 70, 75, I even saw a person in my local store. I think that person is around 80, maybe 85. His back bent over a lot, and I know that he struggles a lot. But the reason why he still works at that age is probably because he does not have sufficient retirement fund. But the truth is that every American deserves and should have sufficient retirement fund, because as long as you do this, the government allows you to do this tax-freely, you will end up with $1 million in your retirement account. Okay, so everyone deserves to be a millionaire, and so as to retire at 60, 65, 70 with dignity. Okay, so this is what I want to teach you. Okay, be prepared. Don't be someone who has to work when you already lose your house, and that is too painful. So be prepared. So reserve kind of like your joy from the cars, which is only going to depreciate. Instead, think about your future, especially when you do not have the ability to make stable income. So that's what I want to share with you. I realized this when I were around 7 or 28, maybe 28. And so I want to share it with you because I think most of you are around 20, 21. So you have a longer time to go to get prepared. Okay, and believe me, so now the average Americans whose age is around 70, do you know how much on average? Do you know how much do they have in their savings account on average?
I don't know, 30 grand.
Around $50,000. With $50,000 in the retirement fund, they have to work. They have to work because even the nursing home, 1 year of nursing home is going to cost more than that. So these people, if they don't work, either they are going to not be able to feed themselves, or they have to totally rely on their children to take care of them when they lose the house. They put all the burdens on their children. So now we shouldn't be the person like that. When we are senior, when we need the care from someone else, we should have the ability to pay for that. We don't want to leave the burden on the ones that you love most. Okay, so that is what I do. Sorry, I just closed my that is what I do. Starting from age 28, I always max my Roth contribution, and also my wife's. We don't want to put the burden on the kids. Same do you. Okay, it's hard. Okay, so that's my lesson to share with you. So any question for me?
Yeah, how do you not have a perfect rate my professor score? Like, this class is incredibly interesting.
Sorry?
How do you not have a perfect rate my professor?
Oh, how do I not have a perfect grade on readmyprofessor.com? So I think I'm not sure. So far, the last time I checked, it was maybe 2 weeks ago. I think at that time I have 49 ratings.
Mhm.
Out of them, 48 is 5-star, and only one of them is like 4 or 3-star. I don't remember 4 or 3, but at least the 3. So actually, I know that student from the comments that he left. I know who it is. I taught that student maybe 2 years ago. That guy is I don't know how to say that. Is nerd a good term or bad term?
Nerd?
So that-
I like being called a nerd.
Yeah,
think
that
it's a
guy.
good term.
Yeah, that guy is really a nerd in math and programming. So I think that he learned all this stuff before he came to my class, maybe even in his high school. So for him, my class is really easy. In my class, he whenever I ask a question, he even initially he replied me, and gradually he stopped to reply me because he thinks that is, I guess he thinks it's too easy for him. So his comment is like, he give me a difficulty rating of 1. it thinks that one give me one difficulty rating. So, and most people give me a difficulty rating of 4 or 3, even 5. So it's too easy for him. But I mean, the reason for him to give me that reason, I don't think it's because I don't teach good. It's because he's too good to take this class. He shouldn't take this class. But I have to take care of the majority of the students in my class. I cannot say customize increase the difficulty level to increase the difficulty to his level. It's going to be too hard for the other people. So yeah.
I mean, he should have gone to like Princeton or Harvard or something if he wanted to.
I don't think he can, because he's bad at presenting himself and expressing himself, and also he's not a team person. So
I know the feeling.
Yeah. So that's why I say he's kind of like a nerd. He's just different. So okay, so I have I see 2 questions from chat area. Do I teach any other classes? Usually I only teach this class. But next semester I'm going to teach 2 sections of 212 plus 1 section of big data analytics, which is a graduate class. So can you lose money in a Roth IRA? Yes. So the question is, can you lose money in your Roth IRA? Yes, definitely you can. So it's possible for you to lose money in Roth IRA. So let's say it's just like your investment on a fund. Let me open up my. So let me explain it a little bit for you, because that's also my interest. So can you present on my screen? Okay, so can I say it?
Yes.
Yes. Mm-hmm.
Okay, so let's say we pick a couple of Vanguard fund, VTI. VTI is the total stock market fund. So let's say if you invest on Vanguard, and let's say you start your investment in early 2020. Let's use it as 1 year. So let's say you invest, you buy it in at this price, 164, and suddenly you say, okay, within 1 month, it dives to 151. So basically, you lose 10% of your investment. That is say it's possible, but it's just in a short term. As you can see, the general trend is that it's to increase. So the longer you are investing, the smaller risk you have. So as you can see, that the general trend of the stock market is just keep increasing. And personally, I did a couple of analysis over the weekend for my. Let me say yes. Front pick and open up it. Open up. So this is what I do. Okay, I analyzed a couple of funds since 1994, and you can say that okay, for me, okay, the general thing I found is that if you only invest in a short amount of time, let's say in 2 years or 3 years, even though you invest on this VESIX, this is a very conservative investment fund. Even though you invest in a very conservative way, you have 6 to 4% of opportunity of losing at the most 13% of your money, your investment, but on average you make 10%. So I'm talking about worst case. But if you invest longer, let's say over 10 years, if you invest in a very, very aggressive way, a very risky way, VGT, this is a technology fund. So with 0% probability, you are going to lose. But on average, you can expect to make around 180% to 270%. Okay, so that is why I say that if you so since now you are young, so since now you are young, so you can leave your money in the market for a long time, so you can go for those more risky ones and go for a higher yield.
Professor?
Right?
Yeah.
Hi.
Did you see the video of the monkey playing Pong? You know, the Neuralink AI? They put a chip in the animal and then he plays Pong.
No, I don't know that. But so I think you are talking about something like letting a robot imitating people.
No. So Elon Musk's company Neuralink, right?
Yeah.
They put a chip inside a monkey and he was playing Pong, the
Oh,
game.
cool.
And I was wondering, I mean, what do you think about that? I mean, that's kind of like imagine putting chips in the mind.
Uh-huh.
I find that risky.
That is kind of like knowledge transfer. So you're transferring the knowledge from a person. So first you extracted they I think their ultimate objective is that they extract the knowledge from someone from a very well educated one and transfer that knowledge to a uneducated person. I don't think it's going to be very promising. That's my I have to say that I'm not an expert in that area, but I don't think it's very promising. So don't worry too much about that. It's just a showcase. Elon Musk is very good at marketing or say attracting the investors. But think about Tesla. So from maybe 4 or 5 years ago, every year he said, okay, next year we're going to have a totally autonomous driving car available. But until now, it's not going. It still is not there, and I don't think it's going to be there in 5 years or 10 years. So it's far from being more mature enough to let a car drive by itself. So yes, don't worry too much about that. It's just a showcase for the investors.
Okay.
That's my opinion. But if you,
But like we
if you
already
that
like
would be a good option. Say
in terms of like autonomous like cars and robots, we already have delivery robots. You know, those who like deliver food and all. So we have like autonomy in one sense. I mean,
yes.
like Waymo, they have self-driving cars already. They're picking up customers, no driver. It's all computerized.
Yes.
I think it's pretty close. I wouldn't say 10 years. I would say it's very close.
No. It depends on the weather. Do they dare to let the car drive by itself during the night? No. It has to do a lot with the research in computer vision. So it's like they install different cameras on a car, and that the camera capture take picture of the surroundings and let the computer analyze where is the road, where is the tree, and where's the person. So if the light is not good enough, say during the night, or if there is a rain, then there is a high chance for the model to make mistake. So it is far from being mature enough to be trusted in different occasions. So yes, so that's what I know. Cause I'm also doing some research in computer vision, so that's what I know. And but for something like delivery bots, let's say if you want, in China, so now 2 years ago I visited China again, and what I found is that they have a big usually people there live in big a very tall apartment buildings. So let's say 20 levels, 30 levels. So if there is a package for a person, so usually in the US it's like there is going to be a delivery man who gives the package, who puts the package in certain mailboxes, and the people come downstairs to pick it up. But over there, what they do is that the delivery man come to the lobby, and there are a couple of so delivery bots over there. So they just leave the package in the bot and type in a number on this bot,
like a locker.
Okay. The bot is going to take the elevator to the certain floor and put the box in front of the apartment for that person So that is doable because it's less risky. It's not going to risk someone's life. But in terms of autonomous driving, we need to play it very safely.
Professor,
Okay.
I know that technology has a long way to advance to be autonomous, but I think even now, I think it's safer to have like a machine than a human, because humans are emotional and they'll make mistakes while driving, or they'll let stress overcome them. So
My opinion is that it's better to have a assisted driving. Let's say now a lot of cars are do have radar cruise control, dynamic radar cruise control, they have lane keeping assistance. So I think now it's better to and also they have the blind spot monitor, which is very useful. What I think is that it's better to let the computer remind person. So it's like a combination of people and autonomous driving. It's safer for now.
I agree.
Yeah. Yes, I do have. So I drove my friend's Volvo, which is very safe car. So it has lane keep assistance. It's like if this is the lane, it is able to detect the lane and
it vibrates.
Yes, it automatically keeps you in the lane. But the thing is, because Volvo is very safe brand. So one night when I drove that car, so I drove one car. So in front of me there is some road work. Okay, I let the car drive by itself. It does not recognize the road work of there. It almost hit it. I have to push the brake pedal very badly, and so as to stop off there. So it didn't do anything, and it didn't even let me know that it does not recognize there is it does recognize there is an object in front of us. So yes, it's a little bit risky, and so you cannot totally trust it. And but it's good, because if you are just using that feature, it saves your efforts, saves your attention. Okay, so I think I have time to take at most one more question. So if you have it, ask now. Okay, no? So if no question, then I'm going to discuss the second algorithm. The second algorithm is called DFS, depth first search. So this is the way for us to do breadth first search. In breadth first search, for example, if this is the source node, we first visit the nodes that are closest to the source, whose distance is just 1. And then next we visit the nodes whose distance is like 2 from the source node. So all these nodes distance are 2 from this node, from the source node, and then we visit the node whose distance is 3 to this node. So it's pretty much like giving a map. If this is your home, you first visit the nodes that are the neighbors, and then the neighbors of the neighbors, and then the neighbors of the neighbors. So this is what we do with breadth first search. But here people propose another way to do that, which is depth first search. So in depth first search, what we do is that, so first, let's say this is the home address. What you do is that first you pick one direction, either go left or go right. And then you keep going in that direction until there is no way for you to go. Okay, so you keep going this way, and then until there is no way to go, and then you come back to your home again and pick another direction to visit until there is no way to go. So this is pretty much like if we're talking about traveling. So first, this is your home. First, you go north. You go to visit all the places to the north of you, and then you come back home, and then you visit all the places to the east of you. Come back home to visit all the places to the south of you, and then to the west of you, and come back home. So you finish visiting all the nodes or all the places. So these are just 2 different ways of visiting. Make sense?
Yes.
Yeah.
Okay, so this is the pseudocode of depth first search tree. So in depth first search tree, we don't have we don't have a source node. Actually, we don't have a source node. But and here we also associate each node with a color and a parent. Color have the same meaning, white, gray, or black, and parent means the same thing. What is the last node that you're going to visit before this node? Okay, but now we associate each node with two more information, D and F. So in breadth first search, D means the minimum distance to the source node, right? Minimum distance to the source node, correct? Correct?
Yes.
But here, this D means the discovery time, meaning the time when we first visit a node. So for example, if here there are two, so here there are two nodes on the right of you. If you go right, so we will pass each node. Sorry, we'll pass each node exactly twice. There are two nodes on your right, so we are going to pass node exactly twice. The first time is when we visit it, and the second time when we pass it is on the way back home. So we are going to visit each node two times. Correct?
Mm-hmm.
Okay. So one time on the way to the right, and another time on the way back home. Okay. So the first time we visit, we say it's the discovery time. And the second time we visit, we call it the finish time or farewell time. That means that we're going to say goodbye to this node. We're not going to visit it anymore. So there are two different times that we can visit the node. The first time we visit it, we call discovery time. So we associate, we use D for each node. We use D to denote the discovery time, and we use F to denote to record the finish time or farewell time. Okay, so that is what we do with each node. And also we set a time. You can take the time as the day. Okay, let's say on day 1 we visit the place, on day 2 we visit the place, day 3 we visit the place. So we set a timer, and each time when we visit the place, we will increase the time by 1. So it's like we spend 1 day just passed by. So this is the general idea of the pseudocode. I'm not going to explain the details of that because so this algorithm is say the DFS visit algorithm is recursive, so it's hard for me to explain the details of that. So I'm not going to do that. But instead, what I want to show you is this. Okay, the general output of this algorithm is here. For each node, it will be able to associate with 2 different times. The smaller one is the discover time, and the larger one is the finish time. It records, okay, what is the time for you to visit this node for the first time and the second time. So let's say for this node, the first time we visit it is at day 1. The second time we visit is on day 8. For this node, the first time we visit it is on day 2, and the second time we visit is on day 7. Okay, so this is the output. The output is the discovery time and finish time for each node. Make sense? Any question?
It makes sense.
Okay, so and some of you may wonder, okay, what does the discovery time and finish time mean? So far, so none of them is like the minimum distance thing. So they don't seem to have any meaning. But we're going to use these 2 different times later, actually next week. So there are some other algorithms which depend on the output of DFS, the depth first search. So we're going to learn them next week. Okay, so and also for depth first search, the only thing that I just want you to know 2 things. First, the outputs are discovered time and finish time for each node. The second thing is that the time complexity is also V plus E. Okay, so yes, so then this is everything that I want you to know about the second algorithm. Okay, depth first search. We only learned a little bit. And so next, you're going to have your homework 7. In your homework 7, sorry, you're going to have homework 8. In your homework 8, you're going to implement BFS. So this one is not too difficult, but it's not too easy. I would suggest you to prepare at least 4 hours for that. Okay. But if you want to earn some extra credit, you can implement depth first search and earn an extra credit of 100 points. Okay, so if you want to challenge yourself, you can implement depth first search, but it's going to take a lot of time. A lot means like we prepare at least 8 hours or so. Prepare at least 8 hours or so, because it's a recursive one. When you debug it, you will have a big difficulty.
So in my mind, the breadth first search, it's like mainly concerned with distance, whereas DFS is mainly concerned with time. Is that the most significant difference?
No, I think for breadth first search, you're correct. It's more limited to distance. Okay, so we first visit the nodes whose distance to the source is 1, then whose distance to the source node is 2, and then etc. etc. But for depth first search, it's more about direction. After we pick one direction, we will go to the end of that direction and then come back. So it's just different orders for us to visit the nodes.
I see. So it's like a vector. It has
Yes.
magnitude and yeah, okay.
Okay, so any other question for me? No problem. Any other question from you?
No questions from me.
Okay, so then that's our lecture for today, and have a good week.
Thank you so much, Professor. Have a
Thanks,
good
Professor. Have a good evening.
Thank you.
Have a
Professor.
good week,
Thank you.
Professor. Thank you.
Thank you.
Wait, Professor, one more question, if you're free.